Good afternoon, colleagues and friends. On behalf of the Vice Chancellor and Principal Professor Nana Poku, it gives me a pleasure to welcome you to the inaugural lecture of Professor Stephen Ojwach. The Vice Chancellor conveys his congratulations and best wishes to Professor Stephen Ojwach. It is an honor and a pleasure to acknowledge the following guests this afternoon: members of Council, members of Executive Management, members of Senate, inaugurants, this afternoon, Professor Stephen Ojwach, family and friends of Professor Stephen, academics, professional staff, students, alumni, and distinguished guests. Good afternoon. A special welcome to our guests from universities and organizations within South Africa, the African continent, and across the globe. Just to give you a little bit of a background of the inaugural lecture within the University of KwaZulu-Natal, inaugural lectures form part of the University Public Lecture Series and may only be presented by newly appointed full professors who have been appointed in academic schools and centers. Inaugural lectures presents an opportunity for showcasing an exciting and groundbreaking research, teaching, being carried out by professors in our university. Each lecture represents a significant milestone in an academic career, providing official recognition of their promotions or appointment to full professorship. These lectures are furthermore an ideal opportunity for new professors to introduce themselves and to present an overview of their contributions to their field, to academic peers, students, research collaborators. Inaugural lectures are also a platform for their celebration of professors' academic achievement with his or her family, friends, mentors, and colleagues. Distinguished guests, it is my pleasure to now introduce the Dean and Head of School of Chemistry and Physics, Professor Ross Robinson, who will now formally introduce inaugurants, Professor Stephen Ojwach. Over to you, Prof.
Thank you, Professor Madan. Good afternoon, ladies and gentlemen. It is my honor this afternoon to introduce our inaugurant, Professor Stephen Ojwach. Professor Ojwach received his Bachelor of Science Honours degree in Chemistry from the University of Nairobi in Kenya. He then followed that up with a master's degree in inorganic chemistry from the University of the Western Cape in South Africa. He then moved on to conduct his doctoral degree in organometallic chemistry and homogeneous catalysis at the University of Johannesburg in 2008 under the supervision of Professor James Darkwa. Professor Ojwach then joined the Department of Chemistry at Maseno University in Kenya as a lecturer in 2008, before returning back to South Africa as a senior lecturer at the University of KwaZulu-Natal in 2012. He rose through the ranks rapidly and was promoted to associate professor in 2017 and to his current position as full professor in 2020. Professor Ojwach has been involved in numerous university services, such as being the discipline representative on the Research and High Degrees Committee from 2012 to 2015. He also coordinated the seminar program for the postgraduate students over the same period within the school. Professor Ojwach was also the discipline academic leader from 2015 to 2021, and he is currently serving on the panel of professors in the Student Discipline Court. To date, Professor Ojwach has successfully completed the supervision of 10 PhD students, 20 master students, and 25 honors students, and mentored 5 postdoctoral fellows. He has an H-index of 26 and over 2,000 citations for his research to date. Professor Ojwach is recognized nationally and currently holds an NRF C2 rating for his research. Ladies and gentlemen, it gives me great pleasure this afternoon to invite Professor Ojwach and our colleague to deliver his inaugural lecture, which is entitled Transforming Gases into Treasures, the Science and Beauty of Molecules. Professor Ojwach, thank you.
Thank you. The DVC and Head of College of Agriculture, representing the Vice Chancellor, Professor Nana Poku, the Dean and Head of School of Chemical and Physics, Professor Rob Robinson, colleagues, distinguished guests, family and friends. Good evening. It gives me great pleasure today to come here before you to share with you my academic journey from the beginning up to where we are today. And it's my pleasure that by the end of the talk, I will have shared my academic journey with you. So in my talk, I will briefly look at my childhood and education life. I know sometimes we quickly rush to our academic achievements, but we know we all start somewhere. I've never met a professor who was not born, or no matter how clever you are, unless you are given opportunity to go to school, you will never get a first class or cum laude. And therefore I will start with that. And then the main talk, of course, is the research activities and the contribution to the science, as was clearly demonstrated by the DVC. And then acknowledge, of course, we work with a group of people. I will acknowledge them. And finally, I will summarize my talk. So I'm sure most people will know me, but I'm very sure that their colleagues would not know where I come from. So I come from Kenya, in the western part, in Kisumu, which borders Uganda and Tanzania. And this is where I spent almost all my early life, from primary to high school. And this life was not that easy as it may look now, because we have to go through a few difficulties here and there. And with that, I'm very grateful to my mother, Melisha Ngesa Ojwach, for the efforts, despite all odds, to put us somewhere. And that's why I'm here today. I know sometimes I joke with my colleagues during the 10 o'clock tea that, why do you close your office to go for tea? But that's because during this time, taking tea or lunch and then dinner was a pleasure, was a luxury. In most times, it was 2 or 1 meal. And that, until today, sometimes breakfast I can easily forgo and wait for dinner or lunch. And therefore, I'm very grateful for my mom, who tried to put everything on the table. In fact, I remember some of the occasions when there was too little food to share among the family members, and she will say, the kids, once you have eaten, then I've eaten. And my only reward to her is to say that, today, my mom, if you eat, then I will have eaten, and make sure that you eat first. I started my primary school in a small school called Barkanyago Primary School. I'm very proud that I'm giving this lecture in South Africa, because they have got a way of defining some of these schools of historically disadvantaged, quintile 4s. You can see what quintile is, that one, from the look of things. And then moved to Ramba High School. And why have I used this slide? It's because I consider this as the most important step or transformation in my life, from the primary to the secondary. And throughout my talk, I will be talking about catalysis. And as a professor, I should be able to relate my discipline with any day life. And if I relate this to my catalysis, we talk of a metal complex, which on its own is not useful. But when we activate it using what we call activators or co-catalyst, then we do get an active catalyst, which can then be active, selective, and stable. And with that, the role of the activator can never be underestimated in this process. And by that, I'm very grateful and appreciate my brother Jackson for being the activator in that process, from the primary school to the secondary school. For now, I can talk of being an active person, if not selective, but also stable. My life as an academic, we all know academics. It's not that easy to be an academic sometimes. We have got papers rejected. Students can sometimes be also that tricky. And imagine if you deal with all those rejection of the paper, and then you go back home and also get rejected or get something that's not nice. And for that, I'm very proud and grateful for my dear wife, Dr. Doti Ojwach, because when I go home, I smile. When I come back to school, I smile. And that makes things quite simple. And my wonderful kids, Will Kinder, Eliza Tandy, and Darlene Johari. Of course, where will you get a good wife? I know I'm a synthetic chemist, but I can't synthesize one. There is only one area that you can get a good wife, and that is from the parents of the same stature. Thank you very much, the parents-in-law, Mr. and Mrs. Okanda. So I'm sure that covers what I normally regard as the beauty of metals. If you look at my title, we talk of the beauty of metals and the science of metals, and the beauty that I do appreciate all this. Now, if I move into the science of metals, which will then now address my colleagues, professors, and students, I will basically, as a trained condition chemist, that forms the basis and the platform of our research. So the fundamental design of new metal complexes, understanding their properties and features, and that will help us to future design more viable systems. And then the first application of these metals is chemical manufacturing, where we produce new materials for either industrial or domestic application. And secondly, we also, of course, we need to be alive. We also apply some of these metals in medicine, and I will demonstrate just a few examples how we use these metals in medicine. But of course, as the human beings, we understand when we produce, of course, we all need cars to drive, but these cars also come with problems. We talk of greenhouse gases, emissions, and then human beings are very complex. We can create a problem and then solve it. So that now brings me to the sustainable catalysis, where we try and develop projects that are sustainable and viable to the environment. So in terms of chemical production, one of my key, which is the most important research area, is in the area of ethylene oligomerization or polymerization. You remember the title talks of gases. So ethylene is a gas, and basically this is the simplest gas in the group of alkenes. It has got just the C2 carbons, and sometimes we can call it the C2 chemistry or the C2 synthesis. So when you convert ethylene into a number of products, depending on the catalyst you use, you can produce a wide range of materials, ranging from fuel. You can see the GTL. When you go to the petrol station, you see a GTL fuel. That means gas to liquid. This is produced, for example, in Qatar. The South African coal to liquid will be CTL or the GTL, produced by the Sasol, and the GTL, mostly the Shell higher olefin process. We know the Shell company and garage. If you increase the chain length of this molecule to C12 or C16, then you get your detergents, surfactants. I'm sure everybody sees those chemicals in their kitchen. And in the same garage, after putting fuel, you talk of oil, the lubricants. So that's a C16 to C20. And you can carry on to produce the waxes and eventually the plastics which we need for our daily life. So in this context, as academics, our main objective is to target a particular product. And this we do by designing a catalyst that can be selective and active for a given system. So like I said earlier, we revolve around the design of the molecule. And in a metal complex, we have got the metal atom and the ligand, we have got the donor atoms. So the key areas here involve what is the effect of the donor atoms? If we change from nitrogen to oxygen, what do we get? What about if we change the metal center from nickel to palladium? And eventually, how does the overall catalyst structure eventually affect its performance? In performance, we talk of activity, how active it is. We talk of selectivity. For example, does it give us the lubricants or the polymers and that? So this is a work that has been going on for over 20 years, and we only have 40 minutes to demonstrate this, and therefore I will only give highlights which will cover the entire aspects of the work by using some of the public that we have produced. So using this design, we have been able to control this depending on the structure. Like you can see from a parallel palladium complex or an NN donor system, we can produce either polyethylene or produce simply C4 butanes. And this is basically controlled by the catalyst structure. And this is the work that we do. And from this, we have got a number of students working on this. You can see in the first paper, Osana Mukoi. In the second paper, George Simbanyamat, who's currently a lecturer. And then with this, we have got a number of work we've done this, and basically highlighting that we are able, in our catalyst design, to get compound that either gets only the butanes, or we can also extend to get the polymers. In the quest of this research, and this is why we call this research, you target something, but you get something different. And this is why we talk of research. Sometimes I know student can come and say, I'm not getting what we intended to do. The answer is yes, that's exactly why it is research. Otherwise, if we get what we know, then we can as well stop there. So we had a significant discovery in one of this research, and this from 2009, that we observed that we form our oligomers, or the C4 and C2, and then this simultaneously, or what we call tandem alkylation, to form the alkyl benzenes or toluenes. This was not what we intended, but this product that we get is equally significant, because if we sulfonate that compound and then we process it, then we get what we call the linear alkyl benzene sulfonates, or the branched alkyl sulfonate, what we call the BABs. And these are very important chemicals. And today, this work basically defines the research group of Ojwach and co-workers, and some contribution from this field. You see, when we submitted this paper in 2009, there was no single paper that had reported a similar work. In fact, by coincidence, there was a paper that was being reviewed that reporting something similar to that. And it's only when we revised the work that the paper by Dyer and Tal also published. You can see it's 2009 and 2008. And from this, because of the uniqueness of this, there was a patent filed for this work, and it's still protected in our name. And to demonstrate the significance of this work in my research group, so I call this the flagship project and its impact. I've just seen a paper recently by Zhang and Wang et al., where they cited 7 papers from just my research group, or our research group. And that demonstrates that this is a very significant work. And that is compounded, or was confirmed by the publication of a perspective of the use of this technology in the field, both in industry and also in domestic work. So basically, this project is quite important to us. And if I might say, we have almost 5 or 6 PhDs from this group and over 40 or 50 papers just from this project. If I move on from that, we also use palladium to add value to olefins. So this is a project that was initiated by the DST NRF South Africa Center for Excellence in Catalysis, and was originally because of Sasol producing a lot of olefins. And these olefins on their own are not that useful. And therefore, the government sought to task us with the objective of adding value to these chemicals. And you can see that by the use of carbon monoxide gas, which we all know is a poison, we are able to produce esters, which is very useful in the food industry. I'm sure after this, definitely a glass of wine and fragrances. I can smell some in the lecture. And we can produce this using the palladium complexes. And one of these, you can see a demo set here, one of these papers published in Applied Organic Chemistry, where we use some chiral palladium complexes to convert a wide range of alkenes. You can see there 1-hexene, 1-heptene, that is a C6, a C7, up to a C10 into the esters, which are then used as a food. So this is another flagship project that we are currently working on, and is part of my mainstream. The next one is the molecular hydrogenation, where we can produce a wide range of oil. So I'm sure some of us don't like these oils, but we all see the sunfoil, very important. So depending on the number of carbon double bonds, you either get a liquid oil. For example, if you have got 2 or 3 double bonds, that's a liquid oil. If you reduce the double bonds, then you make it a bit of a solid, like in the Rama, or what some call the blue band. And that work is performed by adding hydrogen, which you can use catalysts like nickel or palladium to hydrogenate that. And if you want to completely get the hard or the solid cooking fat, like the Kimbo or the Rama, then we do a complete hydrogen. And this is an important aspect, because depending on the saturation, either the oil could be dangerous or harmful. And that we say, for example, you don't need a lot of the saturated alkane, because then there is some fat deposit in the body system. But at the same time, if you want a solid fat, then you have to reduce the saturation. And this is where we come in, where we use a number of metal complexes. And this one demonstrates one of the papers that we have produced, where we use a benzoazole palladium complex. And you can see it's very effective in the homogeneous hydrogenation of alkenes and alkynes. And another important aspect of this work is that in addition to the hydrogenation, we were able to observe that there is some kind of isomerization. And what do you mean by this? And what is the significance? For example, in the fuel industry, if we talk of a linear carbon chain, then that becomes of a low combustion. And therefore, for us to improve what we call the octane rating, we do need to isomerize the fuel. And that's why if you go to the garage, sometimes you talk of, I want petrol 95 or the V power. That with the high V power, meaning high octane rating, it means it is highly branched. But if it is linear, then you talk of a lower combustion. And lower combustion would mean that there is less fuel power in the molecule. So this is some of the work that we are also doing, and we are able to cooperate with some industries to this effect. In the same origination, if we talk of the manufacture of fine chemicals, such as the pharmaceuticals, then we need to introduce something we call chiral molecules. So for chemists, this is not something new. The chiral molecule simply has got 4 different groups on the carbon atom. And this is an important aspect because it's not that easy to design this molecule because they are very similar in nature. And therefore, we have to design a catalyst that is also chiral in nature so that it can convert a substrate, which is a prochiral, to a product, which is chiral. And this is something that we are also working on. And you can see from there, we have got a chiral palladium complex that can produce, that can give, you can see from a ketone to a chiral alcohol. And these are very important feedstocks because of their speciality in terms of the fine chemicals, the pharmaceuticals, or the pesticides, and as well as the herbicides. So that basically demonstrates the 3 areas where the polymerization, the hydrogen, and the carbonation, where we practice what we call the production of new materials using these palladium complexes. Like I said at the beginning, during this production, we do experience some challenges. For example, the use of solvents, which are not very friendly to the environment, or production of waste, which we also don't need. And to respond to that, and according to the UN SGD, we need to have cleaner cities, cleaner environment. And if you don't do that, then you remain behind. And therefore, we have to keep with the new trends. And that brings me to this part 2 of the talk of the metals in a sustainable society. So what is sustainability? It's basically having a process that you can support over time. So if, for example, if you want to order some foodstuff from a given company, then for you to give a tender to this company, then they have to prove that they will be supplying this material. Because you don't have a case whereby today you have your material, then tomorrow or next week it has run out. And therefore in catalysis, this means using materials that are available and with production of minimum waste or minimum environmental pollution. The key features include better atom economy. So when we start with 2 carbons, we end with 2 carbons or even 4 carbons. You don't have a case whereby you start with 10 carbons and you end up with just 5 carbons. So that's why in terms of the carbon trading. So you have to minimize waste production, produce friendly gases and emissions, and most importantly, can we reuse this material so that we don't throw them away. And that brings us to the concept of the circular economy, the loop, where it's a model of production and consumption and recycling, which implies minimum waste. It is the best option compared to the current linear economy of take, make, use, and dispose. So human beings, sometimes we do things that we don't want to be done to us. And if thinking the Bible talks of do unto others what you want done to you, and therefore we are not supposed to dispose, because I'm very sure that for human beings, if you attempt to use them and dispose them, sometimes we see suicide, sometimes we see murder, and therefore we need to adopt the concept of recycling, not disposing everything, and that is the circular economy. So our key strategy here involves the use of available, the AAA, I talk of available, abundant, and affordable. There's a time I attended a conference in Durban. In fact, it's a beach hotel. I won't mention it unless you promise to hire me a lawyer. It's 10 meters from the Indian Ocean. India is full of water, but then each delegate is given just 1 bottle of water. If you run out of that, they ask now to buy. When you buy, it's 50 rand per bottle. So you wonder, we can see water down. Is it not abundant? So it means it was not cheap. It's abundant, but it means not available. So we need something that's available, abundant, and affordable. And the RRR rule is to recover, reuse, and recycle. So this is where we address the concept of sustainability to avoid a lot of wastage. And one aspect where we do this is the use of water as a solvent, because water is considered as the most surface solvent and also abundant. And we're using complexes that are water soluble. So we are able to adopt what we call a multi-phase operation, or you can also call it biphasic operation, where you have got your catalyst in the water phase and your organic molecules in the organic phase. After the reaction, we don't throw away the catalyst, we recycle it and take our product and then bring it back to the system. And as that paper demonstrates, you see that we are able to use this catalyst system in 6 reactions without significant loss of activity. And we can continue using this without having any problem. And that's one of the concepts that is required, because we don't throw away the metal. And I will demonstrate why later, why it is important to recover this catalyst. In the next one, we can talk of magnetic separation, where we take a metal complex and then support it on what we call a magnetic nanoparticle. And that will mean that after the reaction, we bring a magnet, like in this case, we can show the use of a magnet. We can demonstrate that by using this magnet here, we are able, you can see in the solution, it has got the ion color, the brownish. Then you bring the magnet, then all the catalyst which is supported on the ion is attracted to the magnet, and you get your clear solution, which you can then take as your product and recover the catalyst and bring it back to the system, bring again your substrate, and you continue the cycle. And from the data there, you see again, we have got 4 runs. So there are number 1, 3, 4, up to that 4, and then without losing the activity. And this is important because we don't have to buy a new catalyst material, but at least we can produce more and more of that, of the products, without buying a new catalyst material. The next aspect is to immobilize the systems on what we call the silica support. And this is very important because with the silica, it's relatively available and cheap. But then if you immobilize the silica support, then you are able to recover it. This paper is quite significant to us. Why? It's because of the discovery that the porosity of the material largely controlled the catalytic activity of this compound. And this is important because we can infer the mechanistic pathway that takes place in this molecule, that instead of the adsorption, which is normally preferred or the common, we have what we call diffusion controlled mechanism, where the reactants are diffused inside the molecule and react there. So this signal, because in terms of catalyst design, we therefore not need to worry about regulating the surface area by reducing particle size, but instead enhance the porosity of the material to achieve activity. And you can see that with a pore size of 6, we have activity of 372 TON, while we have got a less pore size of 2.5, then the activity is only 296. And this is very important because now, when we want to get better system, remember in catalysis, always the objective is to get a more active system. And therefore, if you need a better system or a more active system, then the whole concept here in future design is to increase the pore size. In terms of availability, you'll see that most of the metals we use are precious metals. We talk about ruthenium, talk about gold, we're looking at platinum. These are expensive chemicals. And therefore, from an industrial perspective, or what we call economic viability, they are quite tricky, and most companies start shy. And therefore, the way to go, or the best option, is to adopt what we call the abundant, the available, and affordable metal catalyst. And if you look at that table, you'll see that manganese, for those who are good in mathematics, you see that manganese is 10 million times more abundant than ruthenium. But if you look at iron, which is the 4th abundant element on Earth, it is almost 500 million times more abundant than ruthenium. So what does this tell us? That instead of using ruthenium as a catalyst, which is quite expensive and also rare, can we then go the iron and the manganese route? And this is exactly what we have done, where we use iron as a catalyst. And you can see here, we have got very relatively good activity for the transfer, the generation of ketones to alcohols. Manganese is also quite abundant. And I'm happy to report here that we were the first group to report the use of manganese catalyst for the transfer of ketones. And this is a very high active system and stable. And that's the significance of this work is clearly demonstrated by the editors choosing it as a cover page of this material. And therefore, this is one of the areas we are dealing with. So we are looking at other systems like the zinc, the cobalt, and I'm just using this as a demonstration to show our contribution to this field. In terms of circular economy, it means you need renewable resources, which can be used and also be recovered. And we call this that we can kill 3 birds with 1 stone. I'm sure you're familiar with the 2 birds. So we can talk about 3 birds with 1 stone, where renewable resources, biocompatible, which means not harmful to life, And also at the same time, we can't talk of biodegradability. And an example of these are the polyesters or the polylactides. So we can take from corn or sugar, you get your sugar, then you fermentation, you get your lactic acid. The lactic acid gives you the lactide, which you can polymerize to get the polylactide. Polylactide is used in the production of so many things that like the plastic cups, the medicinal equipments. And then once you get the lactide, the advantage of this is that once you use this plastic, unlike the normal polyethylene, it can be recycled. And we have got two main methods of recycling. The first one is the mechanical recycling, where you can take and just crush it. But as chemists, we deal with the chemical recycling, where we can talk of pyrolysis, simply meaning heating at high temperature without oxygen. We can also talk of hydrolysis, because of water, or alcoholysis, where we use alcohol. And this is where our research comes in. We use alcohols to degrade the polylactide back to the lactic acid. We call it closing the loop, where we start from the monomer, we get the polymer, we can then produce a material and then recover this material back to where we started, and nothing gets lost in the environment. And a clear demonstration of this is this paper. The technology is also quite good. I've just received the news, I think this morning, that this paper has been accepted. And we have got the zinc catalyst there. You can see on the left, we can polymerize the lactide to the polymer. The same catalyst, that's why you call it the multi-tool. You can also call it bifunctional catalyst. Can also degrade the polylactide into alkyl lactate and with equal activity. But these are very important aspects and currently addressing the issues of pollution and the dumping of waste. And we are pursuing this and giving a lot of interest. Currently, we have got about 3 or 4 students working on this. So the last section of my scientific talk, like I mentioned, was the metals in medicine. These are very important areas as well. And basically, we look at the anti-cancer drugs. We know that cancer is one of the leading killer diseases worldwide. And the mode of treatment definitely depends on the progression, what we can call the stage. So for stage 1, you can basically look at just the surgery where you remove it because it has not spread into the other part of the body. But once it has spread in other parts, then you cannot do any surgery, because now if you remove it from one part, it will go to the other part, then you adopt the chemotherapy. That's the most advanced. Radiation can also work at a mild stage, but once it is at very advanced stage, like stage 3 or stage 4, then chemotherapy is the way to go. And one of the most common metal drugs used here is the cisplatin or platinol at the commercial market. So, but there are some advantages of this platinol, and therefore we are trying to improve the activity or the biological relevance of this platinol. But before that, I will try to be a bit more technical, but in a simpler way, to demonstrate how this drug works, the pharmacokinetics of the drug, that when you take the cisplatin, it has to go through the bloodstream and into the bloodstream, into the cytoplasm. If it doesn't do that, then there will be no activity. And that's why you hear somebody say that I've been taking this medication, but there is no improvement. It means you take the drug, but it doesn't get into the blood system. Once it goes into the blood system through hydrolysis, there are 3 options. The first option, which is what we need, is for it to stop. Remember, when we talk of cancer, we are talking about cells that are growing very rapidly and controlled, where today it could be 1 gram, tomorrow is 5 grams, and it becomes a huge mass. So what you want to do is to stop this and control growth. So once it binds to the DNA, it then stops the growth and you get cured. And this is when we talk of you have undergone remission. And you say, so and so was sick last week, but now it's doing better. Sometimes that doesn't happen. It tries to stop the growth of the cell, and then the cell recovers and kicks out the drug, which means the cell continues growing. So that means the DNA repair. So this is where we have a case whereby you are under medication, you seem to be having improvement, but then all of a sudden you again get worse. So which means that there is something that has happened to the drug. So we talk of, it was doing well last week, but this week not so well. That means that you have undergone the DNA repair. The other option, which the third one, which is not required, which is the side effects, where instead of this drug targeting the cancer cells, it goes to the live cells, the normal cells, which means it's now having a negative impact. And that can bring other issues like you can have other like headache or some unwanted issues. And that's why we talk of, when I take this medication, I don't feel well. So we also need to regulate that so that we just target the DNA, we target the cancer cells alone and spare the live cells, what we call the selectivity index. So how do we go about achieving this objective? We have got 3 questions that we ask. is that can we manipulate the conditional chemistry of our metal complexes? Because as synthetic chemists, that's where we come in to design a molecule that will show improved biological activity. And then is there a correlation between the rate of reaction and cytotoxicity, which means the activity? And is there an optimum drug DNA binding interaction, because you need your drug to interact with the DNA molecule, which then stops the DNA from uncontrolled growth. And we have done this, and the review paper there captures all those three questions, and some specific examples are where we talk of comparing the rate of the reaction of the subunit reaction of the complex and its biological activity. And indeed, we confirm that yes, there is some association. For example, we look at this compound 1, you see it has got a very good activity, the IC50 of 3.9. IC50 simply means that the amount of drug required to reduce the growth of the cell by 50%. So the lower, the better. Remember, these drugs are also have got no side effects. So the lower dose, the better the dose. So you see that at 95,000 per second, we have got a better IC50 of 3.9. But with the low reactivity, like in this case, the 10,000, then the IC50 is 90, which basically not even good at all for a drug. So we are able to demonstrate that we can control the kinetic reactivity of these molecules, and that reactivity activity or the reaction with the other molecules, we can then improve the biological activity of the molecules. In terms of DNA binding, this is one of the most important, the rate determining step, because you need your molecule to bind to the DNA to stop it from uncontrolled growth. And again, we are able to demonstrate that we can control that by having a higher binding constant, giving us better activity. In terms of the research, we also combine what we call the experimental approach with the theoretical approach so that we understand better what we have observed. Because the world is moving towards artificial intelligence, or what you can talk of the fourth industrial revolution. And we bring some in silico studies where we just use computer models to predict what kind of activity we are likely to get, and also what kind of binding mode we are likely to get. For example, in this paper, we are able to demonstrate that this kind of molecules bind through intercalating mode. You can see they are within the cell, and we can then determine which kind of molecule and how the activity will be. And therefore, when we now synthesize them in the lab, we know or can predict what is exactly likely to happen. It takes time to get an active drug in the market. In fact, some of them, like the first cancer drug, took almost 20 PhD students to get. So we have gone through a lot of these molecules. And finally, we are not lost. So we have some success stories in the fact that some of our lead compounds show comparable activity and selectivity to the commercial drug in the market against the HeLa cell. The HeLa cell is basically a cervical cancer cell line. And you can see that if you look at the commercial drug, the platinol, in this case, for the HeLa cell, I got IC50 of 11.4 macromole. The ruthenium complex there shows a far much better activity of just 5.47. That's two times the best. And in terms of selectivity, we see that we have got for the commercial drug is 1.6, while for our compound is SI of 2. What does that mean? It means that if you take this ruthenium compound, it has got the chance of 2 times attacking the cancer cell line than your normal cell, which is a better option, because then you will not have the negative consequences of using this drug. So basically, this summarizes the work that we are currently doing, and all these talks, this comment I've given here, none of them has been done by my hands. It's done by a group of students in the lab and colleagues. And here we have got a number of postgraduate students that are trained and mentored here. So we have got, in terms of human resource development, and one day we'll leave to professors, and what we need that once we leave, the research will not stop there, and other people will continue to talk about capacity building and knowledge and skills transfer. So you can put a name to refer to some of these names. Yeah, if I think Mr. Malema will call them the ground soldiers or ground fighters. So we call them the lab soldiers. Yeah, so these are some of them, the master students, and we have got the PhD graduates here, like the dean mentioned, there are 10 students. We have got Dr. George Amato, current HOD in the University of Embu. Dr. Chabalala, a lecturer currently at the University of Johannesburg. I think Makosonge is at UNISA. We have got Rena here doing postdoc in the US, and the ongoing 6 of them are sitting here, and soon they'll become red. So sometimes we do this thing thinking that we are doing our normal work. You wake up in the morning, you do your normal work. I take my student reports, I mark it and give them back to them. And you know, this is basically my work. But little do we know that some of these routine jobs do have long-term impacts on other people's lives. And I can demonstrate that by using just something from the host mouth in their own words. This is from a former master student who's currently a laboratory manager in one of the biggest chemical companies in South Africa. And if I may read that, it's talking about, I know I'm smart, but I was doing postgrad just because. I really did not have a reason to do it. I didn't even give it my best. I survived and made it. But your guidance and supervision is what guided me. I remember there was a time you gave me extra writing exercises to improve my writing skills. You will be so proud to read a report written by me today. And that did not just motivate me to do better, but made me realize, I think it's a very important sentence, but made me realize the importance of understanding your subordinates' needs and skills, which is one of the things that I am good at and helping me grow as a manager. You have no idea how grateful I am of your teachings and guidance. Thank you. And I say thank you for the appreciation. Of course, I was a supervisor here. Nobody's a supervisor without being a student. And I fully appreciate my mentors. I know Isaac Newton once said, if I have seen further, it is by standing on the shoulders of the giants. So if you see far, it means you are standing on an upper ground. Who's this upper ground? So Professor James Dakwa, my master's and PhD supervisor, and Professor Papoli as well. Currently, I think Prof. James Dakwa is retired. Prof. Papoli is still in the service. I hope he will continue doing a good job. But Prof. Dakwa, even though he's retired, he's very active. Even right now, as we're talking, we are writing a paper that hopefully next year will be published. I have a team that I work with, apart from the students. I also work with the collaborators, because we look at, if you look at the research teams, it cross-cuts what we call the multi and the interdisciplinary. So sometimes we need experience from others. And if I look at the national collaborators, I'll very proud, and funders, I'll have to give cognizance. The Center of Excellence in Catalysis, the DST NRF, what we call the Sea Change. The Sea Change funded my PhD study. And when I got back to South Africa as a researcher, I was one of the PIs absorbed and give a lot of platform, and that contribute Professor Mani Oslo for his work. Professor Marvin Meyer is our biochemist dealing with the anti-cancer studies, and a number of them here are also our colleagues. We also go abroad. Remember, the university is ranked by not just the national outlook, what you call the international standing. So you have to be known what you call the outside borders of your country. And I think we have achieved that. We have international collaborators and funders on different projects. So Professor Vanna Thiel, the Technical University of KwaZulu-Natal in Germany, is on the manganese work. We have got Dr. Fatokun here from the Liverpool John Moss University in the UK, also another biochemist. I'm sure most people here, know Prof. Jaganyi, who was here, but currently in Kenya, also our physical chemist. Professor Soja Harris Police at the RWH, Aachen University in Germany, is working. We are working with her in the circular economy project. We also have colleagues from Kowenje from Maseno University. Of course, life doesn't revolve around colleagues in the lab or the research. We have the wider community, and this, the University of KwaZulu-Natal, we're very proud of them. The College of Agriculture, Engineering, Science, the School of Chemistry and Physics, and I'm sure they have given me good support here, both academic and support staff. The support staff can be very crucial here. I remember sometimes I get stuck in the airport, even on a Sunday, and I call Jeshri to change my flight. Thank you. The NMR, most of our work depends largely on NMR from Craig and Sean, the stores. Of course, man shall not live on bread alone. We need church, KwaZulu Private Church. I'm very grateful and for your presence. And I'm also happy that I'm in South Africa and the Kenya government knows that I'm here. And I'm very proud. And in the presence here, we have got the education attaché from Pretoria to present. And I'm saying thank you, family, which I have not mentioned in the talk, and all friends. And we have God, of course. In the Bible, it says, God's alive. We are all because he is. So without him, we are not present. I can now summarize this talk. I hope I've convinced you and demonstrated to you the role of conventional chemistry and metal complexes in the bulk and fine chemical manufacturing and processing, our contribution to this field in producing new materials, and also how this compound can be used in the development of drugs for medical treatment, e.g. in cancer, the promotion of technology transfers in the patent, knowledge sharing, national and international linkages and collaboration. And I think number 4 is very important, the human resource development, training, and capacity building, and also enhancing a better society, environment, and livelihood. For those who are keen, you will notice that there is someone who is missing, and of course he cannot miss, and I cannot finish without dedicating this talk to my father, William Ojwach. I still remember his last words. I think I was going to do my metric, what we call KZN in Kenya. Here it's called metric. And his last words, but then because he was sick and passed away a few months later, he used to call me Sungura, the Maber, Yori Ler. That's my mother tongue. If you translate that into English, it will say the hair, go well, your future is bright. May God rest his soul. Thank you very much. Asante sana. Erukaman. Yabanga kulu, danke, gracious, mercy.
Safi, Professor Stephen Ojwach. For those who are listening to this talk, all over East Africa and South Africa and the whole world, you will see and realize that University of KwaZulu-Natal is a university of choice indeed. Professor Stephen, you are inspiring greatness. I was so intrigued in terms of the number of areas where you're publishing your work in Elsevier, in Royal Academy of Chemistry, and was so intrigued as a college and as a university, we're so proud of you. Your topic was more of transforming gases into treasure and the science and beauty. And we'll all agree here that it was the beauty of science, and we are proud of you. Now we understand how platinol works, about the cancer issues that we have, and now we understand about the pharmacokinetics and metal drugs, which we are so proud of you. And therefore, on behalf of University Executive Management and Senate and also the Office of Registry, we want to wish you well, and we're so proud. We want you to breed more chemists, and we, as a college, will support you, and will create a good ecosystem, fertile ground for you to operate. And we want to wish you well, and congratulations on your full professorship. We thank you very much, and good luck in all your future endeavors. Asante sana. Well done, Stephen. That was so fantastic.
You.
Stand.
Thank you so much, Pamela. I'm now looking off, and
yeah, thank you, Prof.
we
Thank
we
you.
really enjoyed. We really enjoyed the talk. Ross, you are in a good space. With no doubt. Well done.
I'm just checking we're offline. We're offline.